Bismillahirrahmanirrahim. Assalamu alaikum to all of you. Guys, today I'm going to present the most important lecture on the quick review of real analysis in the form of key points. So you can remind them a night before exam also. In this lecture, I'm following the Bartle Real Analysis book as many of the students over the world using this book. And for the convenience of the students, I'm recording this lecture in English. So let's start the lecture without wasting our time because we have to cover as many as topic we can uh, cover in this lecture. As you guys remember the term real numbers, so we can represent a real number in the union of the rational and irrational numbers, as you know. So the second key point is that our rational number can be represented in the form of p by q, where our q is not equal to 0, and our p and q are belongs to the set of integers, and the condition also is that p and q are in the least form. So the third point is that we cannot write our irrational number in the form of p by q. Now come towards its properties. When we add two irrational numbers, we can get a rational or a irrational number. So in that case, our Closure property doesn't hold. When we add two rational numbers and in answer we must get a rational number. So in that case you can see our Closure property hold. When you multiply the irrational numbers to irrational numbers, in result you will get uh, maybe a rational number or a irrational number. When we multiply two rational numbers in answer, we must get a rational number, so it's also satisfy the Closure property. And similarly these two properties. So next point is very important to my point of view, that is, if we take z and a from the set of real number with z plus a is equal to a, then our z is equal to 0. It means when we add two numbers and in answer we get a number a, then our z must be 0, and it is called our additive identity. Here I'm using this addition as dual addition of numbers. So the next key point is that if I take u and b from real numbers and my u and b are not equal to 0 with u multiplied by b is equal to b, then my u is must be 1, and that is my multiplicative identity. So that is also an important property. And next key point is, if I take a from the set of real number, then when I multiply a by 0 in answer we get 0. So that's so simple, you know. The next key point is that if our a is not equal to 0 and b is also in real number such that our a b is equal to 1, then our b must be equal to 1 by a, 1 over a. So that is our multiplicative inverse. So the next key point is, if our a dot b is equal to 0, then either our a is equal to 0 or b is equal to 0, then this equality holds. Move toward next key point. There doesn't exist a rational number r such that r square is equal to 2 or r is equal to under root 2. So in other words, we can say our under root 2 is not a rational number, or our under root 2 is irrational number. So we can prove it simply by a contradiction. So here I'm not supposed to given you to given you its formal proof, but I will tell you the steps to prove. So here you are given with the proposition. So suppose the negation of that proposition, therefore q and therefore negation q. Hence you can get the contradiction in the form of q and negation q. Thus you can get your statement true. Now move towards the next key point, and that is, let n belong to the set of positive integers and under root n is not integer, then under root n is irrational number. For example, your n is supposed to be prime, then when you take the under root of that prime, so it never become an integer. So in that sense, you may suppose. So in next key point, you can see the formal definition of the set of positive real numbers, in which he says let r is equal to p, and here our p is the set of positive real number and p is non-empty, then p is called set of positive real number if these three properties satisfy, uh, or one property is that if our a and b are from p, then their addition must belongs to that set p. If our a and b belongs to p, then its multiplication also belongs to that set p. The third axiom is that if our a belongs to the set of real number, then exactly one of the following hold. Uh, Either our a belongs to that set, comma a is equal to 0, or minus a belongs to our set p, i.e. the set of positive real numbers. The next key point is that if your a belongs to the set of positive real numbers, then you must get your a is greater than 0 and is called the positive real numbers. If your a is belongs to p union 0, then you can get your a is greater than or equal to 0 and say called it as non-negative real numbers. Next key point is that if minus a belongs to p, then you must get a is less than 0 and you can say you can call it negative real numbers. If minus a belongs to p union 0, then you must get a is less than equal to 0 and you can call them non-positive real numbers. So in this key point, you can see the more properties of real number, and is let a, b and c belongs to the set real number. Then the first property is if a is greater than b and b is greater than c, then you must get a is greater than c. If a is greater than b, then for some c, a plus c is must be greater than b plus c. If a is greater than b and c is greater than 0, then you can get ca is greater than cb. Similarly, you can see the fourth property. The next key point is if our a belongs to the set of real numbers such that a is greater than or equal to 0 and less than some epsilon, for every epsilon is greater than 0, then you must get a is greater than 0. Here we are supposing our epsilon is greater than 0, but very small number. So the next key point is that if a multiplied b is greater than 0, then either a is greater than 0 and b is greater than 0, or you can get a is less than 0 and b is less than 0. The next key point is that if a b is less than 0, then either you can get a is less than 0 and b is greater than 0, or you can get a is greater than 0 and b is less than 0. So those are the some basic properties of real number. Now our next topic is absolute value of real number. Uh, Absolute value of real number a is denoted by mod of a and is defined by mod of a is equal to a if our a is greater than 0. We can get the result a if our a is greater than 0, and we can get the answer is 0 if our a is equal to 0, and we can get the mod value as minus a if our a is less than 0. For example, our this mod value can never be negative. If you put any number in the place of a, whether it is negative or positive, you must get a positive result. So you can see by an example. When you put 2 at the place of a, you must get 2 as a result, positive 2 as a result. As mentioned here, if our a is greater than 0, we get a. So 2 is greater than 0, so we must get positive 2 in result. If we put minus 2 in the place of a, so as our minus 2 is less than 0, when we put our minus 2 in the place of minus a, so minus minus plus, and you will get positive 2 in the answer. Here are some properties of mod, so you can go through it. So our next topic is triangular inequality. So in triangular inequality, if we take a and b from the set of real number, then our this inequality is known as triangular inequality. In next key points, also these inequalities holds in general, where a and b belongs to the set of real number. For geometrical interpretation of the real number system, you can use the real line. You can use the real line. That is the key point. And the next key point is uh, when we have to calculate the distance between 2 points on the real line, then we use the notation a minus b mod. By this you can get the distance between 2 points. Like in this case, you can take the distance between points a and b, and in result you will get a minus b mod. Now in our next key point, we will get the idea of close to. A real number x is close to a should mean that the distance x minus a between them is small, or you can say our x minus a mod must be less than epsilon, where our epsilon is any number greater than 0 and is very small number, you can say. In our next key point, we take the idea of epsilon neighborhood. Let a belongs to the set of real number, then epsilon neighborhood of that a is the set for epsilon is greater than 0, such that you can get a set of that type, where x belongs to the set of real number, and the distance between x and a is less than epsilon. So your all x, these x where x belongs to the set of real number are fall, or you can say contained in this epsilon neighborhood of a. So on the next page, if our x minus a mod is less than epsilon, so you can also write it as minus epsilon is less than x minus a is less than epsilon, and therefore our a minus epsilon is less than x and is less than a plus epsilon. So the next key point, you can also read this key point. This statement is true in general, so you must see this also. So in next key point, if our a b belongs to the set of real number and our b is not equal to 0, then these true properties must hold. So you have to remember these properties for your exams or maybe for your convenience to understand more general concepts in future. So whenever I mentioned, you have to just remind them and just remember the statements as I've said in the above key point. So the next key point is, if our a and b belongs to the set of real number, then the mod of a plus b is equal to the mod of a plus mod of b if and only if our a b is greater than or equal to 0. So you can also remind this. Similarly, you can see the statement below. It is easy to understand them, and if you feel free, so I recommend you to see their proofs from the Bartle book, Bartle Real Analysis book, so you can see from them. So our next topic is the completeness property, and it is the most important property in real analysis. Let S be a non-empty subset of R. The set S is bounded above if there exists a number U belongs to R such that our S belongs to that subset of RS. The small s belongs to S is less than or equal to U, and that U is our upper bound. If there exists some upper bound for some small s belongs to the capital S, then our this set S, that is the subset of real number, is said to be bounded above, where each U is called upper bound of S, and you can see here any larger number than U is also our upper bound. If there exists any larger number than U, then it is also considered to be our upper bound. Similarly, we can say the set S is bounded below if there exists a number W belongs to R such that W is less than equal to small s for all small s belongs to S. The condition is that our W is must be less than or equal to that small number S. So many of that number which are less than that W is also considered to be our lower bounds. And in our next key point, we will see the boundedness. A set is bounded if it is both bounded above and bounded below. That is, S is greater than or equal to W and less than or equal to U. And this S is belongs to that set. I mean the subset of the real numbers. A set is not bounded, then it is obviously unbounded. So in next key point, let S be a non-empty subset of the real number. If S is bounded above, then a number U is called the supremum of S if the two conditions are satisfied, and that are U is an upper bound of S, and if V is any upper bound of S, then this inequality must hold. That is, U is less than or equal to V. If these two conditions are satisfied, then we can say this number U as our supremum. Similarly, if our set S is bounded below, then our number W must exist and is called infimum. We can say W as infimum if our these two properties are satisfied. That are first property is that W is lower bound of S, and if T is any lower bound of S, then this inequality must hold, that is T is less than or equal to W. And in the next key point, you can see the four possibilities for a non-empty subset S of the set R, that are the subset S have both supremum and infimum, have a supremum but not infimum, have an infimum but not supremum, have neither a supremum nor a infimum. In that case, these are some general examples. You can get the set of these types. Also you can see the statement here. Also you can see the proof of it from the book Real Analysis Bartle. Till now, we have just take the idea of the boundedness and the supremum and the infimum. Now we are able to define the completeness property of R, and is every non-empty set of real number that has an upper bound also has a supremum. So that is the completeness property of R. If every non-empty set of real number has an upper bound, also it has the supremum in that set R. So the next key point is that you can also remember it, that S is a subset of R, i.e. that is bounded, and A belongs to the set of real number defined by A plus S is equal to this. Then this equality is true in general. So in this lecture, we just take an overview of the real analysis till completeness property of the real number. So guys, I think this is enough for today lecture. I will continue from here to onward in my next lecture. Thank you so much for watching.